Good morning, my dear students. My name is Dr. K.C.H. Apparao, working as a Associate Professor in Mechanical Department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous class, we discussed the rate of heat transfer in single slab and composite slabs, and rate of heat transfer in cylinder and coaxial cylinders or composite cylinders, and the rate of heat transfer in hollow sphere or and uh, composite spheres also. So we already derived the formulas, rate of heat transfer Q formulas for the slabs, for the cylinders and the spheres also. Also we covered the uh, critical radius of insulation for the cylinders and the spheres also. Okay, in this class we will see the heat dissipation through fins. Wow. What is the influence of fin? What is the advantage of the fin? We'll see. So, okay, what are the different applications of the fins? Also, we'll see, and we'll also derive the rate of heat transfer in fins, different types of the fins. So, long fin, short fin, or insulated end pins. We'll see derivations of all these things. Okay, we know that according to Stephen Bowles, it means Fourier's law, Q is equal to minus Ka into dt by dx. By using this one, we already derived the rate of heat transfer in the slab. So that is the Ka temperature difference T1 minus T2 by L1. Okay, so this one already derived this one. It means Q is directly proportional to thermal conductivity K, and Q is indirectly proportional to thickness of the insulation, the thickness of the slab. If the thickness of the slab increases, automatically rate of heat transfer will be decreases, and Q is directly proportional to temperature drop T1 minus T2. Okay. So also Q is directly proportional to area. Q is directly proportional to area. So K is the thermal conductivity of the material. It is depend upon the material. So if you want to uh, increase the rate of heat transfer with respect to thermal conductivity, it means you have to change the material. You have to choose the good material, just like copper, diamond, like this one. Okay. So next, so our ultimate object is to heat dissipation, increase the or enhance the heat dissipation through fins. So that is that one. It means next one is the Q is directly proportional to temperature drop. It means T1 minus T2. Suppose in case of bikes, suppose we'll use the air coolant system for the uh, dissipation of heat from the engine surface to atmospheric condition. Suppose engine surface, if you take the temperature is T1, atmospheric condition temperature is equal to T infinity. So T1 minus T infinity, we cannot influence this parameter because T infinity is the ambient temperature. So ambient temperature we cannot influence. So we cannot influence this temperature difference. But we can influence the rate of heat area. It means Q is directly proportional to area. If the area increases, effective area increases automatically, the rate of heat transfer will be increases. So this concept, it means the application of fin is depend upon the this concept. It means Q is directly proportional to A. So you will see. So whenever the adequate surface, whenever the available surface is found inadequate, suppose the available surface, so suppose the available surface of the engine for the motor vehicle or any bike, so it is not sufficient to dissipate the heat. So at that time, just uh, so required required quantity of heat with the available temperature drop. So the convective heat transfer coefficient, it is enhanced by the some external surfaces. So it means convective heat transfer means the rate of heat transfer through solid to fluid. It means surface of the motorbike to atmospheric conditions. Okay, so this convective heat transfer is enhanced or improved by adding some external surface or extended surfaces. Those extended surfaces are called as simply fins. It means if you add, if you influence the or if you increase the effective surface area, automatically rate of heat transfer will be increases. Okay, so it means by adding some external surface, extended surfaces, it means by adding this some fins, it means we can improve the effective area, automatically rate of heat transfer will be increases. So this is the principle. Based upon this principle, fins will be worked. Okay, heat transfer by convection. Convection means this is the mode to transfer the heat from the solid to fluid. So here in the bikes, just just heat is dissipated from the engine to atmospheric condition, that is required. Okay, so heat transfer by convection between the a surface and the fluid surroundings. So it is increased by adding thin strips of metals to the base surface. Base surface means surface of the engine. So these thin strips or added strips are simply called as the fins or extended surfaces. Okay. So it means the fin increase the effective area. The fin increases the effective area of the base surface. So by increasing the so automatically this effective area also uh, influences the so to increase the rate of heat transfer. So because of this concept, it means q is directly proportional to area. Okay, so this is the fin. We'll see some applications of the fins where we'll use this type of the fins. We'll see that one also. So these are the some types of the fins. So this is the, this one is the rectangular or plate type fin. Next, this is the tapered fins. We will see some types of tapered fins, and this is the radial plate fins. This type of rectangular plates, like rectangular plate fins, are just we can observe these types of fins in the uh, mm, in the surface of the engine of the any bikes. So just like we can, it means in motor vehicles we will use this type of rectangular fins. Okay, so these radial fins, radial plate fins, we will see, we can observe these types of fins on the electrical motors. So in the electrical motors, this type of fins are used to increase the effective area to uh, so to improve the heat dissipation from the surface of the engine to atmospheric conditions. Okay, so this type of disc fins we can observe, just like this types of fins we can observe on the um, air compressors like this one, and some types of fins we can observe on the transformers, and so we can see some types of fins also. So these are the fins, these types. uh, okay, so finally these are the types of the fins. So we'll see major applications of the fins. These are, we will use the for the economizers for the steam power plants. Next, convectors for the steam power plants we will use. So this type of fins. So in air cooled cylinders we will use the these types of fins for the aircraft engines. In IC engines also you will see this type of the fins we can observe on the surface of the engine, and air compressors also on the top surface of the engine. we will see some types of pins you can observe. So in electrical transformers and motors, just like this type of radial type plate plates we can observe on the surface of the motors, electrical motors. So okay, cooling coils and condenser coils in refrigerator system and air conditioning system. Here also we'll see some types of fins. We'll use some types of fins to dissipate the heat from the body to or engine to atmospheric conditions. Electronic equipments, you can see some types of fins which are attached to the electronic engine surfaces to dissipation of the heat. Okay, so these are the applications and types of the fins. Okay, we'll see uh, rate of heat transfer in the fins. So for that one here, I have taken the one rectangular fin, rate of heat transfer in the rectangular fin. So this is the just like base surface, there may be surface of the engine. So the temperature of that one is the T naught, we can see. Okay, this is the rectangular fin which is attached to the base surface. This is the base surface. Okay, or wall of the or surface of the engine. So okay, the length of this one, the rectangular fin is L, and the width of this rectangular fin is equal to small w, and the thickness of this one is equal to T. Okay, so here just like otherwise you can observe here like this one. So this is the x is equal to 0, this is the x is equal to L particular length. Okay, the base surface, this one is the surface of any engine. So this is the rectangular um, pin. So the length of the rectangular pin is equal to L, and the width of this one is equal to small w, and the thickness of the rectangular pin, so that is a small t. Okay, so and x is equal to L. So this is the at base surface, the temperature is equal to T naught. So at the end of the pin, so the temperature is equal to T infinity, ambient temperature. Okay, so okay, we will take some small elemental area, so which is from distance x from the base surface. So the thickness of the small elemental area is equal to dx. Okay, so this is the small elemental area. Okay, so this is the thickness. Okay, so the thickness of small elemental area is equal to dx. So initially we will derive the derivations for the small elemental area. After that we integrate that one, we will get the rate of heat transfer for the total body. So this is a common concept. We derived the derivations for the slab and rectangular and cylinders also in previous classes. Same principle will apply here also. How to derive the general equation for the small elemental area. So by using that one, we have to find out the temperatures equation, and we have to find out the rate of heat transfer for the entire the pin. So we'll see first of all, this is the uh, small elemental area. Thickness is equal to dx. The distance from the base is equal to x, and the temperature of the small elemental area you can take, that is the T. Okay, so here just like the rate of heat transfer Qx is the entering heat into the small elemental area. So this is the entering heat, Qx is the entering heat into the small elemental area. So then Qx plus dx, this is the leaving rate of heat or from the small elemental area. So next to Q convection, so that is the rate of heat transfer through convection mode. It means in the small elemental area, heat transfer takes place by two modes. One is the conduction, another one is the convection. So this is the entering heat. This entered heat is just like dissipated by two modes. One is the conduction process, another one is the convection process. So you can write like this one: q x is equal to q x plus dx plus q convection process. Okay, so you know the formulas of the qx plus dx based upon the Fourier's law. You can write like this one here. So this is the qx is equal to qx plus dx plus q convection. So you know the formulas for that one. You know that qx plus dx is equal to qx plus dou by dou x into qx into dx. This is the formula. You know that, like, so qx is equal to qx plus dou by dou x of qx into dx plus q convection, the h a area into temperature drop, that is the, it means t minus t infinity. Okay, so area here, so affecting area, that is the perimeter into thickness, so it means p into dx. Dx of this, dx is the small elemental area thickness. Okay, so p is the perimeter. So it means this area is nothing but you can rewrite like this one: h p into dx into t minus t infinity. So this is the formula. Okay, so here qx will be cancelled. Okay, you know the formula for the qx is equal to minus ka dt by dx. Here also minus ka dt by dx plus dou by dou x into minus ka dt by dx, means we can rewrite like this one. This is the minus ka d square t by dx square into dx plus plus so convection heat h p dx into temperature drop t minus t infinity. So this is the just like equation. So this and this will be cancelled, same terms. Then the formula will be like this one. You can see in this PPT already. Written in this PPT, you can observe. So this is the, okay. So qx is nothing but minus ka dt by dx is equal to minus ka dt by dx, because qx plus dx is equal to qx plus dou by dou x into q of x. So qx into dx. So this minus k dt by dx minus k dt by dx will be cancelled. Then minus k d square t by dx square into dx plus hp dx. So because this is the area, t minus t infinity, so that is the value. So then the formula is like this one. Okay, so it means so d square t by dx square minus hp by ka into t minus t infinity is equal to 0. Okay, so this is the equation. Here just like we can take hp by ka is equal to m square. You can show that. So m square is equal to hp by ka, then theta is equal to t minus t infinity. Okay, if you derivative this theta, it means so d theta by dx with respect to x is equal to dt by dx. So this is the t infinity, the ambient temperature, that is a constant with respect to direction x. Okay, so it means d theta by dx is equal to dt by dx. D square theta by dx square is equal to d square t by dx square. You can rewrite like this one. Okay, same value is written here. So d square t by dx square is nothing but d square theta by dx square and minus hp by ka. So just written as a m square into theta is equal to 0. Okay, so this is the just like you know that this equation describes the function of x and m. So this is the second order linear differential equations. You know that if you solve this one just like according to mathematics, you will get the general equation, that is the, so theta is equal to C1 e to the power of minus mx plus C2 e to the power of 4 mx. This is called general equation. Okay, here you can observe this one. So this is the general equation if you derive this one. Okay, so theta is equal to C1 e to the power of minus mx plus C2, this is C2. Okay, C2 e to the power of mx. This is the general equation. So by using the general equation, we can derive the rate of heat transfer. Okay, so the same process we already doing from slab and cylinder and sphere also. Okay, so first of all, we'll see some types of rectangular pins. So we'll see rectangular pins like long rectangular pin. It means the length is very high, so we can take like length, so that length of pin tends to infinity. It's very long. And short pin we can see, and uh, convection of the end pin. So you'll see it means so three types of pins we will see. One is the long pin, another one is the short pin. Short pin is nothing but insulated end pin. This is called insulated end pin. Okay, so it means at the end of the short pin, so it means the rate of heat transfer does not take place with respect to x. So it means this value is equal to 0. That is the boundary condition. Okay, so for next one is the third one is the convection of the end. So it means at the end of the pin, uh, so heat transfer by convection is equal to heat transfer by conduction. That is the principle. That is the convection of the end. We will see that one. So first of all, we will see the long fin. So for these three types of the fins, just like boundary conditions will be varied. Like first of all, we will see the long pin. We will derive the rate of heat transfer for the long rectangular pin. Okay. So here we can observe this one. So this is the base surface. It means x is equal to 0. It is the length of the pin. So it means x tends to infinity because you are taking this the long pin. Okay. So it means x tends to infinity. So at that condition, the temperature at that condition that becomes T is equal to T infinity. Here T is equal to T naught. So initial temperature. We'll see the boundary conditions. Here also I have written this one. Long fin. So it means infinitely long fin. So length uh, tends to so infinity. So very long length. So if the fin is sufficiently long, the temperature at ends equals to the surrounding temperature. It means that T is equal to T infinity. So this is the condition. We'll see the first of all boundary conditions, and we'll solve the rate of heat transfer Q for the long pin. So these are the boundary conditions. That is the x is equal to 0, then uh, theta is equal to theta naught, means we know that theta is equal to T minus T infinity. So theta naught means so at x is equal to 0, T is equal to T naught. So T naught minus T infinity. Okay. So that is represented by theta naught. It means the first boundary condition is equal to at x is equal to 0, theta is equal to theta naught, T naught minus T infinity. You can say this is theta naught. That is the first boundary condition. Second boundary condition, because it is the long fin, so it means if the x is equal to infinity, the x is equal to infinity, so you know that theta is equal to T minus T infinity, the formula. So at x is equal to infinity, it means so T becomes at the end of the pin, the temperature of the end pin is equal to the atmospheric air, air temperature. It means that is the T infinity. It means this T is equal to T infinity, that is equal to atmospheric air temperature. So it means T infinity minus T infinity. is equal to 0. So second boundary condition is equal to at x tends to infinity. Okay, then theta is equal to 0. So 1 is equal to, at x is equal to 0. So theta is equal to theta naught. Theta naught means t naught minus t infinity. At x is equal to infinity, at x tends to infinity. So theta is equal to 0, because t will be t infinity minus t infinity is equal to 0. Okay, so we have to consider these two boundary conditions and apply this boundary condition for the general equation. Then we will get the temperature formula at x distance for the small elemental area. If you integral this one, we will get the rate of heat transfer formula. Okay. So, okay, apply the first boundary condition. So, if you apply the first boundary condition, so you know that general equation, that is that theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx e to the power of mx. Okay. So, if I apply the first boundary condition, what is the first boundary condition? At x is equal to 0, theta is equal to theta naught. Theta is equal to, so theta is equal to theta naught. Okay, it means so this will be theta naught C1 e to the power of minus m into x is equal to 0 plus C2 e to the power of m into 0. So m into 0 means 0, e to the power of 0 is equal to 1, you know that. Then theta is equal to C1, theta naught is equal to C1 plus C2. So that is the equation 1 you can take. Okay, so that is the theta. So then apply the second boundary condition. I will see the second boundary condition. If you apply second boundary condition, we will see what will happen. So you know that this is the boundary condition. Theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. So this is a general equation. So second boundary condition, at x tends to infinity, so theta is equal to 0. Theta will be 0. It means for the based upon the second boundary condition, that theta will be 0 and C1 e to the power of minus m infinity plus C2 e to the power of m infinity. Okay. So here, so e to the power of minus m infinity, you can write 1 by e to the power of m infinity. 1 by e to the power of infinity, m infinity, that value is equal to 0. Okay, you know that one. So then the total term, this term will be 0. So then C2 e to the power of m infinity is equal to 0. You know that e to the power of m infinity never equals to 0. It means based upon this condition, only C2 is equal to 0. C2 is equal to 0. So this is the condition you can take like this one. 1 by e to the power of m infinity is equal to 0. E to the power of m infinity never equal to 0. It is some term. So, but C2 into e to the power of m infinity is equal to 0. So it will not be 0 means so C2 will be 0. So from the equation, from the based upon the second boundary condition, C2 value is equal to 0. Okay. So from the first boundary condition, so based upon the first boundary condition, C1 plus C2 is equal to theta naught. Okay. We got the two equations. So one equation, so first boundary condition, C1 plus C2 is equal to theta naught and C2 is equal to 0 from the second boundary condition. Then C1 is equal to theta naught because C2 is equal to 0. C1 value is equal to theta naught. So substitute these C1 and C2 in general equation. You know that this is the general equation. So theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. Okay. So here theta will be theta naught. No. So this is theta. So theta is equal to C1. So what is the value of C1? That is the C1 is equal to theta naught e to the power of minus mx plus C2 is equal to 0. 0 into something, that will be 0 completely. So the finally theta is equal to theta naught e to the power of minus mx. Okay, so this is the formula. It means theta is nothing but t minus t infinity. You know that here theta naught is nothing but t naught minus t infinity into e to the power of minus mx. Okay, you can rewrite like this one: t minus t infinity by theta naught minus t infinity is equal to e to the power of minus mx. This is the formula. You can remember this one. So if the uh, just distance of the small elemental area from the base, so if you know the x value, then you can find out the temperature T value for that small elemental area. So by using this formula, you can find out the temperature of the small elemental area at x distance, any distance, because T infinity is the ambient temperature, that is constant. T naught is the surface temperature. It means so engine surface temperature, that may be fixed. So by using those parameters, you can find out the T value. Okay. So you can read it like this one: theta by theta naught is equal to e to the power of minus mx, or theta is nothing but t minus t infinity by theta naught minus t infinity is equal to e to the power of minus mx. You have to remember this formula. Okay. Now by using this formula, you can find out the rate of heat transfer in the small elemental area. You apply this one, you will got this one. So this is the final formula. You have to remember this one. Okay. So now, so this is the equation for the small elemental area. Now we'll see the rate of heat transfer in the entire the pin. How to find out the rate of heat transfer in the entire the pin? You know that we have to integral this one. Automatically we will get the entire rate of heat transfer Q. So here Q is equal to, you know that. So this is the convection formula you have here taken. So rate of heat transfer through the convection process, because the rate of heat transfer takes from heat transfer uh, from the surface of the engine to atmospheric condition is done by the convection process, because solid to fluid. So through convection mode, heat transfer takes place. So here, just like convection principle is taken, that is, you know that HA into delta T. So H is equal to, so H area is equal to perimeter of the small elemental area into, so dx is the width of the small elemental area, okay, into temperature drop. So that is the temperature for drop for the small elemental area is equal to T minus T infinity. So this is the formula for the small elemental area. So convection rate of heat transfer convection formula for the small elemental area. If you integral this one with respect to the boundary conditions, x values at x is equal to 0, next x is equal to infinity. So initial length and final, it means initial point and final point of the pin. So it means 0 to infinity range. If you apply this integral for the rate of heat transfer formula, then you will get the rate of heat transfer for the entire pin. Okay, so we'll solve this one. Solve this one. Okay, integral hp t minus t infinity into dx. Here with respect to x only. So you know that this is the formula: t minus t infinity by theta naught minus t infinity is equal to e to the power of minus mx. It means t minus t infinity is equal to theta naught minus t infinity into e to the power of minus mx. Okay, it is the temperature drop t minus t infinity. So in this place you can write this term theta naught minus t infinity into e to the power of minus mx. Okay, here the term is written in the place of t minus t infinity, because t minus t infinity is equal to this total. So then the formula is like this one: integral of hp theta naught minus t infinity e to the power of minus mx into dx. So integral with respect to x, so e to the power of minus mx integral means minus m into e to the power of minus mx. Okay, this is the term. So from this one, integral this one 1 by m, sorry. So minus 1 by m. Okay, so minus 1 by m into h is a constant because that is the rate of heat transfer coefficient. So h p is the constant perimeter, and t naught minus t infinity you can write like to theta naught. So into, so we'll get the e to the power of minus mx. So limits is equal to 0 to infinity. We can apply this one. Okay, minus 1 by m into, so here hp theta naught into, okay, so if you cancel this minus, then limits will be 0 to infinity. You can take like this. Infinity, no need to take. 0 to infinity. Okay, if you cancel this minus, otherwise if you apply this one, this is the minus, like this is the minus. So you know that e to the power of minus m infinity, so that is equal to 0. You already we discussed it previous slide. So it means 0 next to infinity to 0. Okay, if you substitute the 0 value, e to the power of m0, so m into 0 means e to the power of 0. E to the power of 0 is equal to 1. 0 minus 1. Okay, so 0 will be cancelled. Here minus will be so will be positive plus. So then we got this one 1 by m into hp theta naught value. Okay, you know the value of m. So we already taken m square is equal to hp by k. Then m is equal to under root of hp by k. Substitute this value in this one. Okay. So then just I am writing here. It means hp by under root of hp k. Okay. So this under root, this is hp. The equation will be like this one, under root of hp k. So this is the value of this total term into theta naught. Theta naught. Okay. So finally, the rate of heat transfer formula. Rate of heat transfer formula. So Q is equal to under root of hp ka into theta naught. So you have to remember this one. So you know that theta naught is equal to t naught minus t infinity. You can rewrite like this one, under root of hp ka into t naught minus t infinity. So this is the formula for the rate of heat transfer. So Q, rate of heat transfer for the long fin, is equal to under root of hp ka theta naught minus t infinity. Okay, so we'll see one numerical based upon this formula, then you can understand. So this is a small numerical which is based upon the long pin. So calculate the amount of energy required to solder together two very long pieces. Very long pieces. It means you can observe this one. This is the long pin. Okay. So very long pieces of the base copper. So that is the 1.5 mm diameter. So diameter of the pipe has been given. It means area has been given. Okay. So area 5 4 d square. You know that. So and melt at 190 degrees. It means base temperature T naught also given. T naught is equal to 190 degrees Celsius. The wires are positioned vertically in air. Air means T infinity. So ambient temperature of the air. So that is given. That is the 20 degrees Celsius. Assume that heat transfer coefficient on the surface. It means H also given. H is equal to 20 watt per meter degree Celsius, and thermal conductivity K also given. K is equal to 330 into watt per meter degree Celsius. So these are the given data. So you know that you have to calculate the amount of energy required. It means Q, rate of heat transfer. So rate of heat transfer is equal to, already derived this one, under root of Hp Ka into theta naught. So theta naught is nothing but so T naught minus T infinity. So T naught also given, T infinity also given. So H also given, K also given. Area you can find out because diameter is equal to given 1.5 mm. You can convert into meters. Okay. So by using this D, you can find out the area also. And the perimeter P. So you know the formula of perimeter. So that is the pi d for the, because it is in circular rod. So we derived the formula for the rectangular bar. Here shape of the pin is equal to circular bar. So you have to take the areas based upon the diameter. So if you substitute these values in this one, so if you substitute these values, so in this one you will get the rate of heat transfer. So this is a small numerical which is related to previous derived equation. Okay. Now we'll see the second next pin. So that is the insulated end pin. So already I told that three types of pins. One is the long pin. Second one is the insulated end pin. Also it is called as a short pin. Short pin. So or it is called as a insulated end pin. Insulated end pin means so insulated end pin means so at the end of the pin there is no heat transfer. Rate of heat transfer will be zero. It means Q. So change of the rate of heat transfer with respect to X will be zero. Change of the temperature. So change of the temperature with respect to X is equal to 0. Also you can read it like this. D theta by dx is equal to 0. So this is the condition at X is equal to L. So last point of the pin, end point of the pin. So this is the important condition. So here we will see two types of boundary conditions. One is the first one is the same boundary condition, because this is the base. So small pin, rectangular pin is attached to here. This is the base temperature. This is T naught. Here temperature is equal to T infinity. Here X is equal to 0. Here X is equal to, so this is L. So here X is equal to L. Okay. So at temperature is equal to T naught. Here temperature is equal to T infinity. So here boundary condition on the insulated end means d theta by dx is equal to 0. So how to apply this condition here. Okay. So first boundary condition at x is equal to 0, t is equal to t naught. So second boundary condition at x is equal to L, d theta by dx is equal to 0. We have to apply this one. Okay. So you know that this is the previous derived formula. By using this one, we already got that C1, it means general equation. That is general equation is equal to theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx. So we have to use this general equation for the solving of insulated end. So it means solving of the rate of heat transfer in insulated end. So we'll see the best step first of all. So this is the small diagram. This is initial point, x is equal to 0. Here x is equal to L. So this final form. So end point. The length of short pin is equal to L. Okay. So dt by dx. So the condition based upon the insulated end condition for the short pins. So dt by dx is equal to 0. Okay. So it means t tends to t infinity. We'll see that one also. Okay. Here boundary conditions at x is equal to 0, theta is equal to theta naught. Okay, that is the first boundary condition. It means at x is equal to 0, So T is equal to T naught. It means theta is equal to T minus T infinity, means theta naught is equal to T naught minus T infinity at x is equal to 0. First boundary condition. So that is same for the 3 pins. Second boundary condition will be changed for the long pin. Boundary condition, second boundary condition is different. For the insulated end is different. So second boundary condition, it means at x is equal to L, dt by dx is equal to 0. So we have to apply this boundary condition. Dt by dx means temperature does not change with respect to x because it is insulated end. Okay. So apply the first boundary condition. You know that if you apply the first boundary condition, we will get just like so you know that general equation, that is the theta is equal to c1 e to the power of minus mx plus c2 e to the power of mx. Okay. So it means first boundary condition, if x is equal to 0, t is equal to t naught, theta is equal to theta naught. So then based upon the first boundary condition, theta is equal to theta naught is equal to c1 e to the power of minus mx. Mx means m0 plus c2 e to the power of m0. Okay. It means e to the power of 0 means that is the value of 1. It means theta naught is equal to c1 plus c2. So this is the equation 1. You can take this one. Okay. Based upon the first boundary condition, that is the theta naught is equal to c1 plus c2. So that is the equation 1. You can see here. So next we'll apply this second boundary condition. What is second boundary condition? At x is equal to L, dt by dx is equal to 0. Okay. So it means you know that general equation. So general equation, theta is equal to c1 e to the power of minus mx plus c2 e to the power of mx. This is the formula. So theta is nothing but t minus t infinity. Okay. So if you derive to this one with respect to x, it means that is the dt by dx, because t infinity is the constant with respect to x. So that will be 0. Then so derivative of e to the power of minus mx means minus m c1 e to the power of mx. So plus m into c2 e to the power of mx. Okay. So you can take, that is the m is the common term, m minus c1 e to the power of mx plus c2 e to the power of mx. So here we can see that one, minus m into c1 e to the power of minus mx plus m into c2 e to the power of mx. Okay. So you know that based upon the second boundary condition, dt by dx is equal to 0. It means this will be 0. Okay. So this will be 0. Then so we can rewrite like this on this formula, like c1 e to the power of minus ml. So because the second boundary condition, x is equal to L, you can substitute L in the place of x. c1 e to the power of minus ml, cancel because the total value is equal to 0. Then c1 e to the power of minus ml is equal to c2 e to the power of ml. Okay. So then you can write like this one, rewrite like this one, c1 is equal to c2 into e to the power of 2 ml. So based upon the second boundary condition, so we got the relationship value. So that is the c1 is equal to c2 into e to the power of 2 ml. So you know that first boundary condition, based upon the first boundary condition, we got the equation that c1 plus c2 is equal to 0. Okay. So based upon this one, then you can find out you can substitute the c1 value here. It means so c2 e to the power of 2 ml plus c2 is equal to 0. Here we can see like this one. Okay. So c2, then know that c1 plus c2 is equal to 0. So based upon the first boundary condition, so we got that c1 is equal to c1 value, that is the c1 value is equal to c2 e to the power of 2 ml, c2 e to the power of 2 ml plus c2 is equal to 0. Then C2 is equal to 1 plus e to the power of 2 ml is equal to 0. Okay. Sorry. C1 plus C2 is equal to theta naught based upon the first boundary condition. So then C2 is equal to theta naught by 1 plus e to the power of 2 ml. So that is the value. Okay. C2 is equal to theta naught by 1 plus e to the power of 2 ml. That is the value. So if you just we know that C2 is equal to theta naught by 1 plus e to the power of 2 ml, then you can substitute this value in this one, in equation 1, then you will get the C1 value. Then C1 is equal to, you will get C1 is equal to theta naught into 1 by 1 plus e to the power of minus 2 ml. So here just like C1 value, it is, so here we got the C2 value. C2 value is equal to theta naught by 1 plus e to the power of 2 ml. So you know the formula, so that is the C1 plus C2 is equal to theta naught. Okay. Then so how to find out this C1 value? C1 is equal to theta naught minus C2. So theta naught minus C2. C2 is equal to, already got that one, that theta naught by 1 plus e to the power of 2 ml. Okay. So here theta naught is the common term. You can take like this one, 1 minus 1 by 1 plus e to the power of 2 ml. Okay. So here theta naught, take LCM, then 1 plus e to the power of 2 ml minus 1 by 1 plus e to the power of 2 ml. Okay. Minus 1 plus 1 will be cancelled. So then the finally C1 is equal to theta naught into e to the power of 2 ml by 1 plus e to the power of 2 ml. This is the value. So if you substitute this C1 value in equation 1, you will get the C2 value also. Then C2 is equal to, this is the C2. You can rewrite like this one. So okay, if you divide by e to the power of 2 ml, here also divide by e to the power of 2 ml, we will get this one, 1 by 1 plus e to the power of minus 2 ml. So plus 2 ml for that one for C1. So finally this is the value. So that is the 1 by 1 plus e to the power of t cml. Otherwise if you have any confusions, so here just I am repeating this one. So we got that C1 is equal to theta naught into, so e to the power of 2 ml by 1 plus e to the power of 2 ml. Okay. So divide this one. So one term like by e to the power of 2 ml by e to the power of 2 ml. So then this will be, so 1 by e to the power of 2 ml plus 1. This is the value. So 1 by e to the power of 2 ml means, so theta naught into 1 by 1 plus e to the power minus 2 ml. So that is the value. Don't confuse that. So this is the C1 value. Okay. If it is C1 value, automatically you get to C2 value also. C2 value is the, if you substitute that value, and we will get to C2 value, that is the theta naught into 1 by, so 1 plus e to the power of 2 ml. So just to minus here, here plus. So then substitute the C1 and C2 values. You already got this one, C2. Okay. If you substitute the C1 and C2 values in general equation, so we will get that one. So you know that general equation. So that is the so theta is equal to C1 plus e to the power of mx minus mx plus C2 into e to the power of mx. Okay. So if you substitute the C1 and C2 values, so we will get this equation. Theta is equal to theta naught into e to the power of minus m into x minus l by e to the power of minus ml plus e to the power of ml. So this is the term we will get if you substitute the C1 and C2 values in general equation. Okay. And also it is multiplied with e to the power of ml. Okay. This is the final term here, just to have written here, just to go through thoroughly. So okay, so this is the in numerator, this is the common term, this is that one means e to the power of minus ml plus e to the power of ml. Here also e to the power of minus ml plus e to the power of ml. So take common. So it means the formula is will be like this one. Just I am writing theta is equal to theta naught into, so e to the power of minus ml. So numerator is equal, denominator so you can add. So e to the power of minus m into x minus l plus e to the power of m into x minus l divided by e to the power of minus ml plus e to the power of ml. Okay, so this is the formula. If you take this total term by 2, this total term by 2, then just hyperbolic functions will cos h and sin h. So these values will come. So here just the formula, cos h formula is equal to e to the power of minus x plus e to the power of x by 2. So based upon this formula, so this is term is nothing but cos h m into l minus x. This is the term is equal to cos h m plus ml. So because these are the pluses. Okay, so this is the formula. So it means so theta is equal to theta naught into cos h m into l minus x by cos h ml. So this is the value. So you know that you can rewrite like this one, theta by theta naught is equal to cos h m into l minus x by cos h into ml. So you can rewrite like this one. Okay. So you know that theta is nothing but to t minus t infinity. Theta naught is nothing but to t naught minus t infinity. It means t minus t infinity by theta t naught minus t infinity is equal to cos h m into l minus x by cos h ml. This is the formula. You have to remember this one. It means if you know the distance x from the base of the small elemental area, you can find out the temperature of the small elemental area. Okay, you have to remember this one. So by using this temperature formula, you can find out the rate of heat transfer for the total entire insulated end pin. Okay, so for that one, you know that we have to integral that one. So you know that formula, that is the Fourier's law. So that is, so Q is equal to minus Ka into dt by dx. So you can rewrite like this one. Rewrite like this one, minus Ka into dt by dx is nothing but d theta by dx. Okay, you know that theta is equal to t minus t infinity. T infinity is the constant. Then derivative of this both are equal. So you can write like this one. Here we can see this. So we got already this is the temperature equation. It means so t minus t infinity into theta naught minus t infinity into cos h m into l minus x by cos h ml. Okay, so derivative dt by dx, derivative this equation with respect to x, then this will be theta naught. This is the constant. Here l is x is there. Then x means integral of derivative of this means we will get to minus m into, so cos h m into l minus x. Okay, l minus x by, so this is the cos h ml. Okay, so this is the value. It means we can substitute this value in this one. Here also we can take the limits. So limits, that is the x is equal to 0 to x is equal to l. So if you substitute the x is equal to 0, so because the convection of this is the condition at x is equal to l. So here you can take the x is equal to l condition. X is equal to l condition. Just I am writing here. So then the formula is will be like this one. It means so you know that q is equal to minus ka dt by dx. Okay. So dt by dx at x is equal to L. We got that one. That is the is equal to theta naught. This is the value got, theta naught into cos h m minus, just I am writing here. So dt by dx at x is equal to L is equal to, so that is the value. It means so theta naught into minus m into cos h m L minus x by cos h ml. So then at x is equal to L, you can substitute the L here. At x is equal to, we have to apply the x boundary condition at x is equal to 0 boundary condition. So then the formula is like this one. Q is equal to already minus ka into minus m, minus plus m into theta naught into this x is equal to 0, then cos h ml by okay. So derivative, it means cos h in place of sin h. Okay. Sin h m into L minus x. So this means so sin h ml by cos h ml. So that is the tan h ml. The final formula is equal to ka into, so what is m? M is equal to m square is equal to hp by ka. Then m is equal to under root of hp by ka. Okay. So ka will be cancelled. It means so the formula is will be like this one, under root of hp ka into theta naught into tan h ml. So this is the formula for the q. So this is the formula for the q for the insulated end pin. So you have to remember this one. So finally, just like derived two types of the rate of heat transfer of the two pins. One is the long pin, another one is the short pin. Okay. Just I am repeating those formulas. For the long pin, so rate of heat transfer Q is equal to theta naught into, so e to the power of minus mx. So you have to remember this one. So theta naught is nothing but t naught minus t infinity e to the power of minus mx. You have to remember this formula. Okay. So second one, so that is the so Q is equal to, so theta naught into, so here under root hp also. Q is equal to under root hp ka theta naught. That is the formula. So here, so the formula is equal to, so for the insulated end, that is the hp ka theta naught into tan h ml. So these two formulas you have to remember this one. So this is the for the long pin formula, rate of heat transfer formula. This is the short pin formula. It means so insulated end pin formula. Okay, we'll see the rate of heat transfer in the third pin. So that is the convection of the end. So this one, it means at the end of the pin, it means so conduction, rate of heat transfer through conduction is equal to rate of heat transfer to convection. It means minus ka dt by dx is equal to ha into delta t. So this value, so this is equal. So rate of heat transfer through conduction is equal to rate of heat transfer through convection. So we have to use this principle for the second boundary condition. So we'll see the derivation for the convection of n for the convection end pin in next class. Thank you for watching this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.